Hello everyone, we are a member of Group B and we will be presenting our ADM presentation on early detection of curable diabetic retinopathy from retinal images. Our team members are Darshan Gorasia, Purvesh Borkar, Ramya John and myself Sanket Daima. To introduce, diabetes is a disease which affects on different parts of the body, out of which this research focuses on the eyes, which is termed as diabetic retinopathy. Out of 72 million people affected by the diabetes in the world, it is said one third of the population suffer from this particular effect of eyes, that is diabetic retinopathy. Due to such large number of cases, the pathology labs are under enormous pressure to diagnose the patients, and because of human intervention, sometimes it may lead to some error in generating reports and result in wrong diagnosis due to less experience in the field. Also, modern techniques in medical appliances applied generate a large amount of data which makes it difficult to take rational decisions. To answer these problems, this research question is created, which is, can utilization of histogram equalization and CNN along with the transfer learning significantly reduce the model learning time and improve the performance of classifying retinal images corresponding to detection of diabetic retinopathy? The objectives of this research are to identify the early signs of diabetic retinopathy with patients' retinal images by using machine learning techniques and to understand the impact on model performance by using contrast limited adaptive histogram equalization in image processing with CNN and transfer learning. From here, I am handing over to Purvesh to explain the methodology used in this research.
Thank you, Sanket. Now let's have a look towards implementation methodology. We have used CRISP-DM methodology in this project. CRISP-DM methodology is widely used industry standard framework for data mining project. We adapt 5 phases from CRISP-DM methodology, namely business understanding, data preparation, modeling, and evaluation. Now let's understand the data source. The diabetic retinopathy dataset is freely available on Kaggle website provided by Apex, which is a free platform for retinopathy screening. The data source consists of more than 35,000 images, which goes up to 82 GB of disk space. However, for our implementation, we have subsampled 5,000 images due to the limitation of infrastructure. As a part of data exploratory analysis, we found that dataset is divided into 5 class labels, namely non-diabetic retinopathy, mild DR, moderate DR, severe DR, proliferative DR. We noticed that the dataset is largely imbalanced among the class labels. The issue is addressed in the training stage by penalizing minority classes and shall be discussed in details in the upcoming slides. Data cleaning activities like label cleaning is performed so that the class labels having both the image are only processed by the machine learning models. Also, the class labels having similar stage of diabetic retinopathy in both eyes are only considered. Now next, Darshan will explain the pre-processing slides.
Thanks, Purvesh. And from here, I will be walking you through the data processing techniques that we use and overall model architecture. To generalize the model and add variance in the training data, we have used image augmentation methodology before the training start. Images are augmented by zooming and cropping with various other techniques on the actual images. The newly generated blank pixels while rotating images are filled with the nearest fill method. As a part of pre-processing, we have first time utilized adaptive histogram equalization method in medical images. Equalized images are further grayscaled to reduce the model learning overhead. To split image into training and testing set, stratified sampling is being used. While to address the class imbalance, we have implemented weighted class learning, where minority class are assigned with pre-training weights. Now, the images displayed on the screen shows effect of contrast limited adaptive histogram equalization method on the retinal images on the left side, which enhances the contrast in the images, while the images on the right side shows the same image when converted to grayscale. Grayscaled images are directly then pushed to the model for training. Grayscale pixel distribution of the images can be also seen on the displayed histogram picture. Now in this section, we'll understand overall model architecture. We'll first subsample the entire image dataset as mentioned by Purvesh with Gaussian subsampling technique, and trend test split is carried out with stratified method as discussed. We have utilized 20-layer VGG16 pre-trained model to reduce the burden of initial learning, and to extracted weights are used to build CNN. CNN has been implemented on top of transferred weight with one flattened layer and two dense layers. ReLU and sigmoid activation function are used to decide which neuron to be activated, and log loss function is used to calculate the loss in each epoch, and model optimization on the performance with the help of adaptive optimizer called ADM. Further, I'll hand it over to Ramya to present the model evaluation.
Moving on to the evaluation, the model performance of CNN was evaluated against the data set, which was split into the training and testing set of 80% and 20%. From the first graph given here, that is the one of model accuracy, we could infer that the model is not overfitting to the training set, which is confirmed by the gradual rise in the training and testing accuracy. For the training set, the model produced an accuracy of 89%, whereas for the testing set, the accuracy was 88%. On the other hand, talking about the model loss, for the training data during the first epoch, the loss was around zero point 0.9, reducing gradually to zero point 0.2 in the final iteration, whereas for the testing set during the first iteration, the loss was around 0.67, which gradually came down to 0.35 in the final epoch. Thus, we could infer that the overall loss was inversely proportional to the number of iterations. Hence, we could say that the reduce in the loss increased the accuracy since it handled the false classification by penalizing error causing cases. To conclude, we can say that the use of CNN along with transfer learning and other pre-processing techniques like clay provided a good accuracy as well as reduced the computational complexity and time. This project made use of a publicly available dataset downloaded from Kaggle, wherein the data was completely anonymized at the source level itself, thereby adhering to the GDPR compliance rules. Thank you for paying attention.